The motion of a spinning top has captivated people of all ages from all over the world for centuries. Yet few understand the underlying physics that goes into their favorite toy. Today we'll expand on the physics of a spinning top in order to appreciate the beauty of its motion. All of the physics of a spinning top comes from three conserved quantities. Angular momentum is conserved, both along the orientation of the top and about the z-axis of the top. The total energy of the system is also conserved. Later, we will expand on how these conservations create some interesting phenomena in the top's motion. If we simulate our top using spherical coordinates, its motion occurs in two directions, theta and phi. Shown here are the equations we will use to calculate and update theta and phi. The equation on the bottom can be rearranged to find theta dot, which can be integrated to express theta in terms of time. Now we'll consider the two moments of inertia of our top. If we look at our top with a conical shape, the moments of inertia are dependent on the cone's mass, height, and radius. I-33 passes along the height of the cone, and I star is along x and y. Properly calculating I star and I-33 will be essential for a proper simulation. Here we will define the essential constants, initial conditions, and conserved quantities of the top. We use a while loop to update theta, theta dot, phi, and phi dot. We use an if and else loop to prevent this argument from becoming negative. If it does, we return theta to a stored value and flip the sign of theta dot. If not, we update the position and axis of our cone normally. Now let's consider a fun and interesting feature in the top's motion, precession. Precession is the change in orientation of the rotational axis of a rotating body. For a top, it is how the top's body spins around the z-axis while its tip remains fixed. The simulation window shows this example of precession for our top. Precession can also be explained using Euler angles, but I will omit this discussion for simplicity, but also because Euler angles are difficult to code. If we zoom in on our precessing top, we can see some interesting results. Note the material used, which is helpful for viewing rotation. Our top's point of contact indeed remains fixed in a point. Also, our top's path traces out a circle. With friction present, the top will begin to swing out a wider path before eventually falling. Note, though, that this is an ideal case without friction. Even more interesting than precession is the physics of nutation. This is the fascinating effect of the top's ability to defy gravity. Let's observe our top's nutation before we go into the underlying physics. Watch as the top bobs up to prevent it from falling down. So how does it work? As gravitational potential converts to kinetic energy, the top falls in the theta direction. But due to energy conservation, it also sweeps out in the phi direction. This causes the top to come back upwards before it can fall. If we zoom in more closely on our top, we see the bumps in the top's path caused by nutation. With nutation and precession combined, we get this looping motion in the top's path, although it's harder to see, but is diagrammed here. Let's review. To make a good simulation of a spinning top, make sure to consider the three conservative quantities, L3, LZ, and energy. Make sure to have the proper moments of inertia, and I would suggest a cone. Use an if and else loop to update theta and phi. Then, appreciate the system's nutation and precession. Thank you for watching. I would appreciate any comments or questions you have about tops and how they spin.